In this set of video notes, we're going to add time-varying sources to Maxwell's equations. And by sources, I mean currents and charges. When we're talking about Maxwell's equations in differential form, we're usually talking about current densities and charge densities. So current densities, how much, and charge densities, kilos per cubic meter, for example. Charge density is something that we used to think of as just a function of where you were in space, x, y, z. The new thing we're going to bring is time varying. Okay, same thing for current density, amps per square meter. If we're talking about current flowing through a bulk object like a resistor. New thing, time varying. Before this, we just had steady currents. We could have a current flowing and it had to stay constant with time. And now things are going to change up a little bit. And the link between electricity and magnetism was discovered by looking at time varying behavior. When a current was suddenly switched on or off through a wire, it induced a magnetic field that caused a compass needle to jump. And that was described using Lenz's law. We might have seen this in an earlier physics class where we had an electromotive force. Okay, we're really going to use units of volts for this. It's a voltage. That started up when there was a changing magnetic flux. You might remember, flux is kind of a generic term. It's taking a quantity that's a density and integrating it over a surface. How much is this magnetic field flowing through the surface? Magnetic flux. Magnetic flux density right here. Okay. This whole thing is Lenz's law. Okay, so if your magnetic flux, I need to give examples. This is coming from chapter 9 if you're in my 473 class and you're using the Sadiku book. We need to do some examples because we're talking about a surface integral of a quantity, and how that can change with time is if your magnetic flux density is changing with time, or maybe the extent of your surface is changing with time. How can... Let's get that red marker again. Flux. This whole thing right here. Oops. This whole thing right here. Change with time. Okay, a number of ways that can happen. You might remember from an earlier physics class an example where you have a constant magnetic field, and we're looking at a magnetic field in a plane. We're looking down on it, the magnetic field is pointing into the plane, and we have a system that's like a copper U-shaped thing, and we've got a slider bar on it. And you remember these kind of problems. So it's sitting on there, and it can slide. And that's an example where the magnetic flux, the magnetic flux density, B, could be constant. It could be coming from a permanent magnet. The B dot ds, now we're starting to think of doing this integral, and we're going from x equals 0 to x equals 3 centimeters or whatever. Y equals 0, y equals 3. We're doing dx, dy, integrating over this thing. And if this slider bar is moving, well, now suddenly our x range in our integral, our limits are changing. So that's one way that you can have a constant magnetic flux density and still have an induced current, because you're changing the whole entire flux integral with time. You're changing something here or you're changing something here, and it all goes into this number that you're getting at. It's changing with time. And you're generating a voltage that, how I remember there's a minus sign on this, is we're always trying to oppose. We're somewhat lazy. We're always trying to oppose the change that's happening. We're reacting to it and going, no. And we're going to induce a current that's going to create an opposing magnetic field.